In this exercise, we consider the problem of maximizing 120x plus 80y subject to x less or equal than 40, y less or equal than 20, and 20 times x plus 10 times y less or equal than 100, where x and y must be values greater or equal than 0. We must write the problem in standard form and calculate a basic feasible solution and solve the problem graphically. Indicate if it has any solution and how many solutions, which are those solutions, and which is the optimum objective value. To write the problem in a standard form, I leave the objective function for later and I go to the constraints. The first one is x less or equal than 40. To write it in a standard form, we must transform this constraint in a constraint with the sign equal. So, as the part on the left is less or equal than the part on the right, I must add a slack variable to get an equality. Now I do the same with the second constraint. I call this slack variable x2h equal 20, and finally the same with the last one, 20x plus 10y plus x3 over 8 equal 500. Now the variables are x, y, x, I, h must be greater or equal than 0. And then I come back to the objective function, that is 120x plus 80y, and I add the new variables with a null coefficient. So this one could be the problem in standard form. To calculate a basic feasible solution, we must consider the feasible region of the problem in standard form and then calculate the technological coefficient matrix, which in this case is 1 for the x, 0 for y, 1 for x1h, 0 for x28, 0 for x38. Now the second row is 0, 1, 0, 1, 0, and the last row is 20, 10, 0, 0, 1. Where the variables are x1, x2, x1h, x2h, x3h. As the canonical basis is formed by the columns P3, P4, and P5, then the basic variables are x1h, x2h, h and x3h, and the non-basic variables are x1 and x2. Remember that for a basic feasible solution, the non-basic variables must be 0. So we have that x1 must be 0 and x2 is 0 as well. And then basic variables are calculated by replacing those values at the constraints. So we have in the first constraint, we have 0 plus x1h equal 40, so x1h is 0. In the second constraint, we have 0 plus, x1h is 40. Now, yes, in the second restriction, 0 plus x2h is 20, so x2h is 20. And finally, in the last one, 20 times 0 plus 10 times 0 plus x3h is 100, so x3h is 500. So the final answer is that a basic feasible solution is 0, 0, 40, 20 and 500. For the graphical solution, first we draw the straight lines who will be the frontier of the feasible region, which are x equal 40, y equal 20, and 2x plus 10y equals 500. As we have that x and y must be greater or equal than 0, we only draw the first quadrant of the R2 space. Then we draw the feasible region defined by all the constraints. Then we represent some straight lines of the levels of the objective function. For example, this straight line here is 120x plus 80y equal 1000. This one is the level of 3000. So we arrive at the conclusion that the optimal objective value is on the straight line in yellow color, this one here, and that the optimal point is this vertex in the feasible region, point P. To know the coordinates of point P, we solve the system, the equation system formed by the straight lines y equal 20 and this red line which is 20x plus 10y equal 500. So the solution of this system is x equal 15 and y equal 20. Then we replace those values at the objective function and we have 120 times 15 plus 80 times 20, which is 3,400. Therefore, the maximum objective value is 3,400 and it's reached when x equals 15 and y equals 20. Finally, as P is exactly on the lines y equal 20 and on the straight line 20x plus 10y equal 500, we can say that restrictions second and third are saturated. However, the first restriction, x less or equal than 40, isn't saturated. as 25 units are left. 25 is the difference between the right-hand side and the left-hand side.